Welcome back to Balvigyan Bharati with Abhilash Sarkar. We already have crossed almost at the end of the fluid dynamics. There, uh, presently we are discussing on Bernoulli's theorem and their application. Till now, we have shown two application. One is your venturimeter, through which you can measure the flow. The next one is the Torricelli's law. There we have learned the speed of efflux. In speed of efflux, we have learned an arrangement where we are uh, we are allowing the fluid to flow through an opening. It's a very tiny opening with respect to the cross section of the tank or the reservoir. The condition is that the pressure on the both end, that is the tank is open and the pressure at the both end is atmospheric. Now if the condition is such that if the tank is closed, as I already given an example, in case of a water supply in household, that tank is basically is not kept open, that is being closed to avoid the contamination from air. So if that the arrangement were then in that case what would be the velocity of efflux? So let me uh, take the subject velocity of efflux basically condition if tank is closed. Till now we have seen the same condition when the tank is open. Now the only changes will come if the tank is closed. That need, let's see this be the opening, okay, through which the fluid will flow. This is the opening. This is the closed tank, and there may be at up to this level the liquid or the fluid, whatever you say, is, and this is fluxing this way, okay, maybe somewhat like that. Okay, now what would be the velocity? So one only thing is that instead of having the atmospheric air, the pressure here, it definitely have some pressure. Okay, this pressure is called the vacuum pressure or the not exactly the vacuum pressure. It can say the vapor pressure, basically not vacuum pressure, is vapor pressure. Why it is so? Because the liquid, we know this, if it is liquid, if there is a space on the top of this, there is a chance of evaporation of the liquid due to the temperature, because this is getting temperature from all around and this being dissipated to the liquid, and it will cause to evaporate, because we know there is a natural process of a liquid to evaporate from the top surface, and there is no escape route from that, because the vapor is lighter in weight and that cannot go into the liquid to come out from the liquid. So this will be entrapped here, and due to the continuous evaporation, this space will be it will be packed with so much of vapor molecules, and it will cause to increase the pressure continuously. Okay, so there will always be the temperature, and basically in the daytime the heat received is more, so it will evaporate more and there could cause a vapor pressure here and there it is atmosphere. So the equation, instead of the pressure here it is a atmosphere, only pressure that will act is the vapor pressure. Apart from that, everything is same, half rho velocity square. If I say v1 and this is 0, as I said earlier, because comparative cross section is very large to this tiny hole, and this is kinetic energy rho g, and this time also we are taking this is h. If we take this atmospheric pressure plus, so we'll call it P0 as we did in earlier cases, plus half rho, and V2 we are taking as V, because this is not 0, this is having some velocity of efflux. This is, we can say it as VE, because in physics V is having some other meanings, so we will not put it like that, let it be V. Okay. So plus rho g, and if I take this is the outlet point, so the reference point to that height of this point is 0. So if I take h2, so this will be 0. Here it is h1, I say. So h1 is the height from the reference, so h is equal to h1, so we can call it h. So what are the differences getting? PV plus rho g h is equal to P0 here plus half. This is the ultimate thing will remain. So we'll put it like that: vapor pressure minus P0 is equal to half rho V square, and this I will keep because I need this to be calculated. So remaining thing I will keep one side, half rho V square. So what is your V square then? Rho by 2 by rho will multiply. So 2 will go there, PV minus P0 by rho plus 2GH. Rho will be cancelled out. So this will be a V square. So now I'll take this part of the board. So ultimately V is equal to that velocity of efflux in case of a closed tank, it will be PV minus P0 divided by rho plus 2GH. Okay, so this will be the remaining thing. Now you can understand one thing. So normally if I take this part, this as a whole, it is coming, V is the velocity of efflux for the case, but generally practically it has been observed that for a closed tank the value of vapor pressure is much higher than this value, because this is also a pressure head, and this is caused due to the head difference between the discharge point and the surface of the liquid. So comparatively this is much more than, so this part is approximately taken as 0. Normally this is in general, I am saying practically it has seen that the vapor pressure here is comparative to the head, the pressure head here is, this is the pressure head, kinetic head already is 0, this is pressure head comparatively to the vapor pressure is much less. So this ultimately can be said to be vapor pressure minus atmospheric pressure by rho. This will be the case. Okay, so so this is the ultimate velocity of efflux in case of closed tank. Okay, so we will move to solve further few problem on this theory that I have taught you in last 2 classes, including this, because what we learned Bernoulli's theorem. We already done some problem solving. Then after velocity of efflux and their different aspect of that, range and the time of fall and time to empty a tank, and this velocity of flux in case the tank is closed one. So on this different subject, we'll do some sum right now. Okay. The first of the sum I will do is the level of water in a tank is 5 meter high. A hole of area 1 centimeter square is made at the bottom of the tank. The rate of leakage of water from the tank of water from the hole, from the hole is how much? You can take G value as 10 meter per second square. Okay, so let me read it out once again. The level of a tank, level of water in a tank. This is time the fluid is said to be a water. Okay, tank in 5 meter height. The hole is 1 centimeter square made at the bottom of the tank. The rate of the leakage of the water from the hole is how much? So, as this is not said to be open or closed, we can take the advantage of seeing it as an open tank. Okay, because otherwise there could be some misinformation regarding the vapor pressure. As it is not there, vapor pressure we cannot assume, because this is variable. This is depends on the temperature. So as because this kind of information is not there, we can take it as a, so there is a hole at the bottom. Okay, we can take it as a hole taken at the bottom. This is evacuating. There are some liquid level. It is said to be how much? 5 meter high. The height is 5 meter is equal to h is equal to height 5 meter. The hole is, the cross section is equal to 1 centimeter square. This is in centimeter square, so this is how much in a meter square? 10 to the power 4, that will be the meter square. So 10 to the power minus 4 meter square is the area in SI unit, because this is given in SI unit. Other things also is given in SI unit. So I am using the rate of leakage of water from the hole. So rate of leakage of water means we need to have flow rate. Rate of leakage means the flow through this area. The flow through this area is equal to cross section into the velocity. Okay. So now we have to have velocity. So we can use the energy conservation. So what is the case? We know. Let me go theoretically. I am not putting the formula directly. So what is the energy here? This is atmospheric air there plus half rho, the velocity here could be 0, then static head rho g into h, this is equal to 5. Okay, on the other side, this is also in atmospheric pressure, half v, and you can take it as v, I am saying because I have taken it as v here, so I will put it v here. So half v square, so this is v square plus rho g and h, because I am taking this reference, so will be 0. So this will be the equation. This is cancelled out, this is already 0, this is 0, so this term and this term is remaining. So what is there? Rho g into 5 rho g is equal to half rho v square. Rho also cancelled out, this is g. Okay, so v square is equal to 10 g. So what is that? 10 into 10. So what is your v? 10. Because everything I have converted into SI. So what is your velocity? Meter per second here. So now use the equation 1. So as you have already v is equal to 10. So I am putting it, v is equal to 10 meter per second. Now put the cross section is 10 to the power minus 4 meter square into v is your 10 meter per second. So what is that? 10 to the power minus 3 meter cube per second. This will be the answer. Okay. So the rate of leakage? The rate of leakage is 10 to the power minus. Now you can convert it for getting a countable amount of liquid. If I convert it into centimeter cube, so that will make some sense, because 10 to the power minus 3 will not be so much of means accountability, cannot assume how much it is. So if we convert into centimeter cube, so that has to be multiplied with 10 to the power 6, because 1 meter is 10 square, cube means, so that is equal to centimeter cube. But what is centimeter cube? Basically, cc means 1000, 1 liter equal to 10 to the power 3 cc. So now this is centimeter cube per second, so that means 1 liter per second. So now this will make some sense, because somebody practically can assume what is 1 liter about. 1 liter of bottle, we drink water within a bottle. So 1 liter of water per second, it is going out of this hole. So this will give you some picture how much it is going. So sometimes it may not needed, but if it is there is no choice is given, you can make some sensible answer, so that the examiner or who is checking your copy have some what can I say, impression on your knowledge. Okay, so sometimes it may not need it, sometimes you can put it if time is there. Okay, so if you put like that, so people will make some assumptions, oh, this much of leakage. Okay, so we'll move on to the next problem. The next problem is a little different. A small hole of area of cross section 2 millimeter square is present near the bottom, near the bottom of fully filled open tank of height 2 meter, taking g equals to 10 meter per second square, find the rate of flow of water through the open hole through the open hole. Okay, find the, okay, this is the sum. So this is of similar kind from the last problem, but only thing is you shouldn't be confused because this is something, the language is bit changed. What is the language? A small hole is present near the fully filled open tank. So it is not saying that the hole is at the bottom. Instead of that, it is saying present near the fully. This is the whole area which is present near the fully filled tank. Area cross section near the bottom. Yeah, sorry, I missed this language. Near the bottom. Okay, so only language is being changed. Instead of the hole is being in the bottom, it has said present near the bottom. But then this case also we can take a open tank. Okay, and the cross section of this is this much, height is 2 meter. Even if it is, the height is only given as a 2 meter of the tank and hole is near the bottom, how can this height can be utilized? Means I mean to say, in first case when we are talking about, we have taken at some height, the hole is taken some height, and water level to that tank there is a height, and the hole there is a whole height of the water or the fluid having difference. So this two height is coming in picture, but we cannot calculate or cannot establish some other height because only one height is being given, the height of the tank, the open tank of height this much. Section the present near the bottom, fully filled means tank is fully filled. So if I take the hole is there, so this height, the complete height of the tank which is fully filled, how come it is being used? Because this height there is no clue. So where that hole? This could may student confused after reading. So there will be possibilities if I am not looking at the bottom, instead nearby this could be a point which will also have equal effect. Instead of putting the hole at the bottom, I can put touching the bottom of the tank, extending it, and I can put immediately. So this will evacuate the total water, and if tank is fully filled, so I can take the complete height as a height for the equation. So there is no chance of mismatching the information and my ideas. If I confuse with this, I will definitely be confused. because near the bottom, so near the bottom could be this also, but you can see there is only one height being given set. So how come this can correlate with both the situation? If the hole is there, instead of at the bottom, somewhere where the bottom is matched with one of the surface of the hole. Understood? Now the rest of the thing is same, where the velocity square is equal to what we are getting in the last problem, 2gh. This was the case because nothing is contributing anything. Rho and rho already in the last math you have seen that is being cancelled out, that is not taking part. V here is 0, V here this is one V1, and this is the potential energy of the column. It is converting into the kinetic energy. From there V square is equal to 2gh. So now this is all simple. So this is equal to 2 into g is equal to 10, and h is equal to how much? 2 again, isn't it? So this is your V. So V is equal to 40. V square is equal to 40. So V is equal to under root of this, and the cross section. Now the requirement is the rate of flow. The rate of flow is Q is equal to cross section into V. So that is equal to cross section is equal to 2 meter square. So this is given 2 into your 40. So that is equal to 4 will come here. So 2 again, 4 root 10. So this will be the case, and this is in millimeter square. So okay, sorry, I have to calculate this 2 millimeter square. So at least I have to bring it in centimeter square. So that is equal to 2 into 10 to the power minus 2 centimeter square. Okay, not actually, this is meters, this is meter per second. Now I have to work on this bit. 2 into millimeter to meter, so 10 to the power 3, 10 to the power minus 6 meter square. This is the area. So what we have to use, and this V is equal to 2 into G is meter plus second. So meter per second square G, and H is equal to, is given 2 meters. It's fine. So this is meter. So meter cube per second. This is okay. 10 to the power 6, 2 into 10 to the power minus 6 root 40 meter square area 2g meter square. V is equal to meter per second square. This will come as meter per second. Sorry, this will be meter square altogether. So V will be the square root of this, so meter per second. So this is equal to your area, this is meter square into meter per second. So this is meter cube per second. Ultimately it will be meter cube per second. So this will be 2 will come out to 4 into 10 to the power minus 6 root 10. So this kind of answer will come in meter cube per second. So now we can convert into to cc, centimeter cube. So meter to centimeter cube, that is only 10 to the power 6, that will be cancelled out. So this will be, if I move it like that, this will be centimeter cube per second. So that is equal to this much centimeter cube per second. We can get the answer like this. Okay, so this will be the volume, and this is the flow rate is equal to this much. And now the flow rate is given, so we can assume this is the volume flow rate. In case mass flow rate is being mentioned, so we have to multiply this with rho, the density. Don't forget to do that. Flow rate, if it is nothing is mentioned, so you can talk about the volume flow rate. Now in case specifically mentioned mass flow rate, so this has to be again multiplied with rho density. Understand? Fine. So I will end up here this session. In the next session I move on to few more problems from 3 onwards. Okay. So thank you for now. Bye.